Let's begin. We've got lots of fun stuff to talk about today. I'll be collecting Lab 7 from you during lab, and I have your graded Lab 6 right here. I graded them this time. I'll have some comments about that in a minute, but hopefully we'll get some time while you're working on an example where I can give you back the rest of these papers. The Lab 8 that we're going to do today is the Venturi meter Bernoulli's equation experiment, and I've got the device back in the lab I'm going to bring in just so we can go over some of the basics here in a moment. Group B will be at 2 o'clock, Group A at 3. And then your next assignment is due on Thursday. So this is a 4-hour class, remember. So that's that extra hour that you get for taking this class. That's why there's so much work and you're always busy. And it's either a lab report or a homework assignment or a quiz or maybe all three. So it's busy. All right, let's talk about the labs, and there's something specifically I want you to be aware of, and that is for the data tables. Does everybody have a copy of this spreadsheet that I printed out? Everybody have one of these? You should always paste and format a nice data table and put that into the body of your report. And so you should have a data table. In addition, you should print out and include in your appendix a copy of your spreadsheet where you actually did the calculations. And so here's a copy of an experiment that goes along with hydraulic engineering. You won't do this experiment this year. It's a rectangular weir. And so you'll notice that there's 6 different runs, and I'm calculating, I've got the volume that was collected and how much time it took, and so with that I calculated flow rate. Now you already know how to calculate flow rate based on the experiments we've done so far, but if you'll notice below the table I explain what's in every column, I guess except for run. I didn't explain that, but that's obvious enough. So you'll notice volume. I'll explain here in a row. It explains all those values, what it comes from. And so volume is measured by watching the water level rise up on the glass tube when the plug was inserted into the drain. So I explain how that volume column was developed. And then time of collection, I explain, measured with a stopwatch, quantifying the time has passed as the water level rose between 2 volume marking points. Okay, now on Q, there's a formula that goes along with that. And so I explain that Q actual is volume divided by time of collection. It's nothing fancy. I mean, you don't have to paste like a beautiful graphical equation there. It's just that when I'm grading a lab report, if I see that you've made mistakes in your calculations, I'd like to know how you did those calculations so I can give you some partial credit. Maybe you did something right. Maybe it wasn't like a total loss, like a disaster, or just like a blimp crashing into the ground. Maybe it's not that bad, and if I see what equation you used, then that'll help me to understand what part of it you did get right. And so in most of your lab reports, I indicated either in the comments that I wrote on the report or in the grading sheet that you need to include a spreadsheet that has the equations for each column in your calculations as they go through. And so this just, each one of these columns has a row beneath the table that explains where things came from. So that's what I mean by put in a table of observed data and collected data into the body of the report. So most everybody did that. This is actually what you measured in the lab. And you also need to have a table of calculated results into the body of the report. And I wish I had my document camera, because one student in particular did a really nice job of combining these two together. And actually, I kind of prefer that. I'd rather have one data table that has both the collected data and the results all together. And I wish I could show you that example because it was beautiful. It had the percent error, the average percent error by run. It was perfect. But in addition to those two, very few of you, there were a handful, there were a few that attached the spreadsheet in the appendix, and there were even a couple who had picked up on the fact that I'd like to have a row-by-row description of how each column is calculated. So now you know, no uncertainty about that. But then from the beginning, I've also in the in the rubric it says to discuss the directionality of the results. And I've been getting the feeling that a lot of people don't understand what I mean by the directionality of the results. So look on this handout, the average experimental C sub D. C sub D stands for discharge coefficient. It's like related to energy loss. And so in this particular lab, we were trying to find out how much energy is lost as water is moving from one place to another. So there's an experimentally determined C sub D, and then theoretically how much the C sub D should have been. And if you look at the average experimental C sub D, you'll see it's 0.73, but theoretically it should have been 0.77. So that means on average, the experimentally observed discharge coefficient was lower than what it should have been when we predict it based on the theory that governs how you would develop a C sub D. And so in italics beneath those two figures, I just made a little note to myself. It's really, I put that note in so that I'd remind myself to write it in the lab report. On average, the experimental C sub D is less than the C sub D should be based on theory. So directionality means, you know, you can calculate percent error, but is the value too high or is it too low? And why is it too high or too low? So in this case, the theoretical, if we assume that theoretical is correct, and that's what I say on the far right column, percent error of the experimental C sub D, assuming the theoretical C sub D is correct. So I have good confidence in this formula that's predicting the theoretical C sub D. It should have been, the average of these should have been 0.77, but the average was 0.73. So that means on average, the experimental C sub D is less. So why would it be less? So I need to explain in my discussion why is my experimentally observed discharge coefficient too low. And one reason for that might be that in this particular lab, there's more energy loss. If you have a lower C sub D, that means more energy is lost. And it's probably because the equipment in there, it doesn't have a very sharp edge on it. You have less energy loss if it's more of a sharp edge. And so it could be because the equipment doesn't have a sharp edge. It could be related to the fact that the table wasn't perfectly level like it ought to have been. So when I start getting reports from here on out, I'm going to be looking for if your discussion goes beyond just telling me what the percent error is and explain what it means if it's too high, too low, and how you tie that into the theory. You know, the theory in this lab report is energy losses. And so why was there more energy loss than the theory predicted there ought to have been? Any questions about that? All right. In general, I was really pleased with the lab reports. I thought that you guys are really making solid progress. There's a lot to like in the lab reports, and so, I mean, there's obviously room for improvement. To get to outstanding, that's a pretty high goal. I don't expect everyone to be outstanding all the time. Satisfactory means I'm satisfied. Outstanding means, wow, I'm kind of impressed. You went above and beyond to get an outstanding. You shouldn't expect to see outstanding all the time. Sometimes the mindset is, well, I usually get 100% on my homework. Well, the absence of a mistake isn't enough to get outstanding. To receive outstanding, it's got to be beyond just factually correct. It has to be somehow exceptional to receive outstanding. Outstanding, that means you're standing away from the rest of them. It's, you know, beyond what's typical. So if we go through the rubric just briefly, I'll mention a few things I noticed as I was reading the reports. If you want to be outstanding in your introduction, you have to explain the context of the experiment. You have to explain the experiment and provide an introduction in the concept of the course's theory. And so if it's about metacentric height, the outstanding introduction is going to somehow relate this particular experiment to what we've learned about stability of floating bodies in the course. You know, what is the application of stability of floating bodies? You know, like what's the broader view if you take a step back and try and tie it all together. For outstanding, when it comes to the equations, all of the equations will have the variables identified, and most people are doing that. But then also for outstanding, it says that the equations should be clearly explained. And so maybe in a very short paragraph describing how the equation is used or what the purpose of it is. So not just defining each variable, but explaining how that equation is going to be implemented during the experiment. For method, when we're talking about equipment, the outstanding rating would be given if you identify all the equipment including accessories. And so you may not have thought about it, but the scale that you used to weigh that floating pontoon was one of the equipment resources that you used during the experiment. And so if you mention the scale and you identify its model number, and that's typical in technical writing, is that not only do you say what your data was, but you'd also say where you got your data. And you go so far as to say what's the model number, who made the equipment, and so on. So it may be an arm-filled F1 hydraulic bench, and I don't know which scale, or sometimes the scale is called a balance. In some of your reports I said, what's the balance model number? That's what I mean by balance, is it's what you weighed the pontoons with. So that's one comment I had for the equipment resources. For the method, what I give you in the handout for the method would not be considered outstanding. I intentionally, in the method description on the handouts, I give you just enough that you still need some additional familiarization that you learn along the way. The reason why I don't make the method really detailed is I find that students would sort of get lost in all the details and not go so far as to read a full page of method. So if you want an outstanding method in your report, you'd have to sort of supplement what I provided in the handout with what you learned as you were conducting the experiment. You know, if you're going to remind yourself, if you needed to do this experiment 3 years in the future, what did you learn? Like, what was the trick to finally getting that pontoon to balance on the string? You know, like, what sort of tips and tricks would you have for that future self on how to do the method that maybe just the bare bones procedure that I gave you wouldn't have identified? You didn't need to create your own data table for this experiment, or actually for most of them. Okay, results, when it's a tabular summary of data, we've just talked about how your tabular summary of data that's in the body of the report should have the collected data and the calculated data, and then the appendix should be the full spreadsheet including equations and column descriptions. The results, most of the time it seems like I was giving out marginal ratings on the results, and I would underline because discussion of the two is limited, meaning the discussion of theory versus experimental results is limited. If you want to have an outstanding rating on your results description, you need to dig into the directionality. And if you just find, like, I don't know what to say in my results, you know, here's the table, the end. Sometimes I felt like that when I was a student. You know, I didn't feel like I had that much to say with the results. Well, what you can do is talk about, you know, is the data too high, is the data too low, and explain why it's that way. So me asking this of you actually opens up the door of giving you an idea of how you can expand the discussion of results that you've got. And so you need to plausibly explain the reason for the error. And so what's implausible? I noticed one set of calculations where they were, like, the theoretical metacentric height that is calculated using the theoretical equations. Maybe metacentric height is 0.07 roughly. And then the student had a metacentric height experimental of 0.007, so off by an order of magnitude. And the reason they said that it might have been different is because the ruler you're using isn't very accurate. I mean, that's not plausible. For an order of magnitude to be off by a factor of 10, the fact that you're using a ruler that can only measure to the nearest millimeter, and that's not a plausible explanation. The truth of it was that that student had error in their calculations. And so by plausible explanations, sometimes in past semesters they would say, well, they would chalk every error up to the stopwatch. Like the person using the stopwatch wasn't accurate enough. Like, I mean, maybe they don't have the best reflexes in the world, but certainly it's to within a second. So like 1 second out of 20 seconds is going to introduce like 4% error at maximum. And so they'd always say stopwatch error for like maybe a 30 or 40% error. And that's not plausible. It couldn't be that this person has such bad reflexes that it's like, okay, stop. 1, waiting, click, you know. So I think you get the idea there. So those are just some of the things I wanted to tell you as I looked through the lab reports. Again, you know, I thought you're really on track to getting to where you need to be, and I was happy about that. Please let me know as you read through your lab reports and look at the grade. If you've got any questions, you can stop by during my office hours, and I'm happy to talk to you about the grading that I did on that. So this is just a reminder to my future self that I should give you that spreadsheet handout and point out percent error can be negative. Like, why are these values negative? It's because theoretical is correct and my experimentally observed data was too low. And so if this is the true value and what I observed in the lab is below that, then my percent error should be negative. That means that the observed value is less than the true value. So you can see here where I explain how to do percent error. So it was the percent error of the experimental C sub D, assuming that the theoretical is correct. You always have to make some assumption about one of the two values is the right one if it's percent error. All right, we're talking about acceleration today. What are the two kinds of acceleration we've already discussed? Local and convective. Local acceleration goes to one kind of flow and convective acceleration goes to the other. Do you remember which goes with what? These are different kinds of acceleration. And then they are associated with a certain type of flow. Okay, so local is the change in velocity with respect to time. Okay, so what kind of flow is varying with respect to time? Steady versus unsteady. So when there's local acceleration, we have unsteady flow. If there is local acceleration, that causes unsteady flow. If there's convective acceleration happening, then what kind of flow have we got? Non-uniform, which is the change of velocity with respect to position. Good. That's a good review. This centripetal or radial acceleration is the kind of acceleration that is associated with rotational flow. Does everybody have a copy of the notes, by the way? Everybody's got the notes? Okay, so we're going to be talking about rotational flow today. And here in this figure, it shows that if you have some particle rotating about an axis, and it's rotating with a radius of r, and it has an angular velocity, omega, in radians per second. If it's spinning around in a circle and it makes one revolution, how many radians has it gone through? One revolution is how many radians? 2 pi radians. So sometimes in problems like this, you're going to get the problem statement would be given in RPM. And you'll notice from the equation there that you need to be able to do your calculations in radians per second instead of RPM. And so we'll take a look at converting between the two. RPM, which is revolutions per minute, and radians per second. So if you have, for example, 100 RPM, 100 RPM. That means you've got 100 rotations per minute. So one rotation is 2 pi radians, and 1 minute is 60 seconds. So if we have 100 revolutions per minute, and we multiply that by 2 pi radians per revolution, and then we multiply that by 1 minute in 60 seconds, that allows us to convert 100 revolutions per minute into, in this case, 10.47 radians per second. Now, radians is a somewhat unitless unit. If you think about what happens when you multiply them together and multiply by radius. We know that acceleration, local and convective acceleration, both had the same units. In SI, it was meters per second squared for both of them. Meters per second squared. So local acceleration is when the flow velocity is changing with respect to time. Convective acceleration is when the flow velocity is changing with respect to position. Both of them has the same units. Here, radial acceleration is also going to have units of meters per second squared. And so where does that come from? Okay, so the formula is going to be radians per second squared times the radius. And so radius would be units of meters. And so if we have radians per second and square that, and then multiply it by units of meters, what we're going to end up with is meters per second squared. The radians just go away. It's kind of like a unitless unit. So when we're doing problems today, the radial acceleration omega needs to be in terms of radians per second for us to find out how the fluid responds to that. And so what happens when we start spinning water around? This is a, it's called a U-tube. And before there was the computer site YouTube, there were these U-shaped tubes that were used in illustrations of radial acceleration. What do you suppose? You can see it's rotating from this part of the diagram. It's very clear. It's rotating about the left leg because of that little circular arrow there. Before it was rotating, the water level was at the same spot. But when they started rotating this, the water level rises on the outside leg. Why do you suppose that happens? Why is the water level rising over here on the right? Yeah, and that's on this section and also on all of the liquid. There's except that liquid that's right at the axis. The liquid is responding, and what we said before is that the pressure increases in the opposite direction of acceleration. So when it was this truck full of liquid, when we accelerated the truck this way, the liquid level rises like that. Right? That's obvious. If you hold a pan of water and you accelerate to one direction, the water sloshes in the opposite direction. So if the acceleration is that way, then the increase in pressure is this way. And so, you know, at the bottom of the tank, when the water level is like this, then the pressure is higher over here. So high pressure, and here is low pressure. So in the opposite direction, in this direction, we can say pressure is increasing. Pressure is increasing the opposite way of the acceleration. So does that apply here? In this figure, it's saying that the radial acceleration is in towards the center. the acceleration vector is towards the center of the acceleration here. And so in this case, it's spinning around. The acceleration is inward towards the axis of rotation. The increase in pressure, or in this case, the increase in depth, is the opposite of that. And so it's still, what we learned before is still holding true, which is reassuring and convenient. That acceleration is causing an increase in pressure or water elevation in the opposite direction of the acceleration. Here is the equation that we're going to use in problems like this for rotational flow. What it says is that you can find out how either the pressure or the water elevation or both responds to an acceleration. And here the acceleration is because of the rotation. Omega is causing an acceleration. And if you know the axis, the radial distance from the axis of rotation, the R1 and R2 are measurements of how far away at a certain spot you are from the axis of rotation. And in this particular case, we're going to use this example to calculate what's going on with the dimensions that are identified here. Later on, when you learn Bernoulli's equation, you'll realize it looks really similar to this. But this is not Bernoulli's equation. Although it has two of the terms in common with Bernoulli's equation, it's not the same thing. So let's use this figure and the dimensions that are given to try and calculate what is the rotational rate that's causing what we observe. We can calculate omega and then determine the acceleration that's caused in the right leg because of this rotation and the location of the fluid a certain distance away from the axis of rotation. All right, so to get started, we need to identify a couple of locations. Just like when we were doing the hydrostatic equation, it was convenient for us when we were doing the hydrostatic equation to start at the surface of the water. Like when we were doing a problem and it was like, what's the pressure here? A good place for us to start when we were doing the hydrostatic equation was at the interface of the water and the air. And why was that a convenient starting point? Yeah, it's because the pressure here at location 1, we know it. We know that the pressure there is atmospheric. And so then we'd go down into the fluid using this as our starting point because, we're starting off in a position of knowledge. We do the same thing here. When we have to pick locations, the rotational flow equation says there's location 1 and location 2 in this formula, and we're just comparing how things are at location 1 and how things are at location 2. It's convenient to pick where you know something as the locations. Don't just pick like some random spot in the fluid. It'll still be true. This formula still applies for this is 1 and this is 2, but we don't know what the pressure is right there or right here. And the dimensions don't refer to this location and that location. So we'll be a lot better off in solving this problem if we say, well, let's have this be location 1, which is convenient because we know it's vertical deflection from here and here. I'm not going to draw on it, but you should, on your notes, put location 2 is right up there. Should I do it? Should I do it? No, I'm not going to do it. All right. So if those are our two locations, if this is location 1 and that's location 2, then let's see what we know. We know that the pressure at 1 is 0. This tube is open to the atmosphere. When you're doing rotational flow problems, you need to look carefully. Is the tube open or is it enclosed? Because totally different problems. This one's open. How do we know? Because the top of the tube is open. Subtle clues like that make us strong engineers. All right. We also know the pressure at 2 It's open to the atmosphere. There's no lid above that. Okay, so it's atmospheric. I'm going to, you'll notice that there's a z term in this equation. I'm going to say, let's let z1 equals 0. It doesn't matter. I could have made the bottom of this U-tube my vertical datum, but that wouldn't be a strong starting point because I don't know how far location 1 is above the bottom. So it's just simpler if I say, let's make this water surface be 0, and so therefore if z1 is 0, z2 is going to be 0.25 meters. And I just get that from the drawing. All right. What about the radius, R1 and R2? It's talking about how far away is it from the axis of rotation. So here is my axis of rotation. The drawing shows that. It's spinning about this axis. No, I'm not going to do it. Okay, so R1 is 0, and R2 is 10 centimeters, so 0.10 meters away from that axis of rotation. All right. Finally, what else is it? What other variables are there in the equation? Well, G, so easy, we usually don't write it, except for, it's easy except for when you unexpectedly switch into traditional units and start writing 9.81 when it should be 32.2. And the way to avoid that, of course, is to always write the units in every step of the calculation. And then that 32.2, when you start writing 32.2 feet per second squared, then you'll say, no, I don't, you know, there's a mismatch there. You'll figure out your own mistake if you always include the units. The other thing, well, the unit weight of the liquid. In this case, this is, does it even say what's in here? It's water. It is water. It turns out that we don't even, in this problem, we don't need to know that it's water, but it is water. So we'd use 9810 newtons per meter cubed. And finally, we don't know what the rotational rate is. That's what we're trying to find. What is omega? Okay, so we'll write the equation here. P1 divided by gamma plus Z1 minus, got to make sure that's a minus there, omega squared R1 squared divided by 2G is equal to P2 divided by gamma plus Z2 minus omega squared R2 squared divided by 2G. How come it's not omega 1 and omega 2? Why is it the same? Why isn't there a separate rotational rate for those two different locations? Yeah, that's one object, and it's spinning through the same number of radians regardless of where it is. So if we had like, so if we had a baton and we're spinning it about, you know, like 2/3 of the way, it was spinning a baton, even though this has a higher velocity in terms of meters per second because it's got a longer radius and it's sweeping through a larger arc, it's still both sides of that baton pass through the same number of radians every second. Because if we look from above, if you're spinning this, a line that's being spun passes through the same number of radians, whether it's one side or the other or anywhere in between, even though those at the further end are sweeping through a larger area or passing through a larger distance, still has the same the angular velocity, passing through the same angle. So that's why we don't say omega 1 and omega 2 over on that side of the equation. It has the same, since it's one solid object, it's spinning at the same rotational rate in radians per second. So we don't know what that rotational rate is. So let's start substituting things into the equation. It's going to make things easy really fast because the pressure at 1 is 0, That eliminates this term. Z1, we're saying the elevation of that left leg, the water surface in the left leg, is 0. So that eliminates this term. R1 is 0. So that eliminates this term. P2 is 0. So all we're left with when we reconfigure this equation after canceling out various terms is Z2 is omega squared R2 squared divided by 2G. And we're trying to find out what is the rotational rate that's causing this deflection that we're observing. What would cause a deflection of 25 centimeters? That's what we're after. And by the way, now you can see why it doesn't matter what's in the fluid, like whether it's mercury or water, is that once we cancel out terms, there's no more unit weight term in there. So we rearrange this for omega. We get omega is the square root of 2g z2 divided by r2 squared. That's to the 1/2 power. Okay. So we can substitute in the numbers that we've got. It is 2 times 9.81 meters per second squared times 0.25 meters divided by 0.10 meters squared to the 1/2 power. Okay. So if you do those calculations, we get that it's 22.15 radians per second. Oh, wait a minute. There was no radians to begin with. Where did that radians come from? It just magically appeared. Just like how they magically went away before. Now they just magically appeared. So what units are here? Okay, we got meters squared, and here's meters and meters. So those two, the meters all cancel out. So all we're left with is seconds squared, and that's in the denominator. But then we take the square roots, and so now it's just seconds. So the units are inverse seconds. The angular velocity is 22.15 seconds to the -1, which we interpret as 22.15 radians per second. So if we wanted to convert that into RPM, how many RPM is that? That's a classic quiz question, is to throw in like the RPM / radians per second combination so that you have to calculate one and then switch it to the other. So 22.15 radians per second, if I divide that by 2 pi radians per revolution, then I've got that there's 3.525 revolutions per second. And then I multiply that, 3.525 revolutions per second, by 60 seconds per minute, and end up with 211.5 revolutions per minute. That is the rotational rate that caused that deflection. Are you nodding in agreement, or is it just the weird chairs? Yeah. Okay. He was nodding his head so vigorously. I like that. That's better than this, but all right. Now, what about the acceleration? How many meters per second squared does that go along with? So part B asks, find the radial acceleration. The formula for radial acceleration, A sub r, where r means radial, is omega squared times the radius. Now, it's the radial acceleration in the right leg. So over here, at a radius of 0.1 meters away from the axis of rotation, then it's got, now I'm going to put it back in the normal 22.15 radians per second squared times 0.10 meters, and that is 49.05 meters per second squared. That's a lot of acceleration. This is spinning really fast. Sometimes when it comes to like pilots or astronauts flying, they classify how much acceleration the pilot is experiencing by G's, like how many times the equivalent gravitational acceleration is the pilot experiencing. And if we did a similar thing here, if we said, you know, that particle of water that's over in the right leg, how many G's does it experience? The way we could find that is if we have 49.05 meters per second divided by 9.81 meters per second per G, then that tells us that we've got basically 5.0 G's of acceleration. So that's a lot. Pilots can fly around and maybe get 10 G's, but if they go beyond that for more than a second or two, they start to black out and lose consciousness. So that's your first attempt at rotational flow. Any questions about this example? So like, what common mistakes do students make? Like, I've given a lot of quizzes over the years, seen a lot of exams, and the common mistakes for this are forgetting that it's a minus for this the third term, and then I don't know, I guess that's the most common one. Let's take a look at another one, and I'm going to ask you to try this example with a partner, or if you prefer you can work it individually, but now the tube is enclosed. So what that means is that the water's not going to slosh around like it did in this example. When the tube was open, the liquid that was inside the tube was not constrained in terms of where it could flow. Since it's now there's this liquid is all the way in here, and it is filled with oil. So I give you the specific gravity of the fluid. But because there's a lid on the top, the liquid can't slosh around, but still the pressure changes. And the pressure increases in the opposite direction of acceleration. Okay, so before I ask you to start plugging numbers into the equation, let's just talk through a couple of things that go along with this. If it was static conditions, if it wasn't spinning, where would the pressure be higher? At M or at L? L, obviously, because it's lower down. So that part of it would tell you, yeah, the pressure should be higher at L. Now, what about the axis of rotation? Think about how does a point that's right here compare to a point this L? Which one is going to experience more acceleration? This point on the right or at L? More acceleration. Remember, what we found from here is that acceleration is, they're both going to have the same rotational rate, but one of them has a larger radius. So location L, since it's further away from the axis of rotation, the pressure of the liquid at L would be bigger than the pressure of the liquid right here. So those are just, you know, that's like sort of what's going on here, is you've got an elevation difference and you've got two different radius, the radius of 38 centimeters and the radius of 13.3 centimeters. The nice thing about the rotational flow equation is it takes all of that into account. This term takes into account the elevation differences and how pressure changes because of that. The third term takes into account the radius differences between the two. And so what you should do is just using location L and location M. And by the way, it doesn't matter which is 1 and which is 2 here. You know, in Euler's equation it really did matter, but here it doesn't. Those two locations are interchangeable. So plug in what you know, solve for what you don't know, make assumptions along the way, such as where is the elevation datum. And while you're taking a crack at that, I'm going to hand back your lab reports. All right, so in this one, we've got two different locations. In the solution that I've written up on the board, I'm saying let's call L1 and let's call M2. So I've converted the rotational rate from 25 RPM into an equivalent number of radians per second, 2.618 radians per second. Z1 will be 0, R1 is 0.38 meters, Z2 is 0.125, R2 is 0.133 meters. Rearrange the equation to solve for P2, which is really what we're after, is what's the pressure at location M. And ultimately get that the pressure at M is going to be 1339 newtons per meter squared. So it's a lot of algebra and substitution between the two. Any hang-ups or questions about this example? If we look at the concepts involved, the message you should get is that even though the liquid level isn't allowed to rise or fall in this enclosed U-tube, the pressure still changed because of the acceleration. The pressure in the fluid was affected by this rotation. How do we know this tube's enclosed? Because it's not open at the top. All right. Very good. You're learning. All right. Do you remember when we talked about vapor pressure? Did we watch a video of water boiling at a low temperature? All right. So in this case, we've got a, now we don't know, it never said if these were absolute or gauge pressures. Probably it's gauge because it didn't specify. But if we spun this thing hard enough, we could get the pressure at M to go below atmospheric pressure. And if we were measuring this in absolute terms, we could spin it fast enough that actually there is a negative gauge pressure, and we could make the liquid pressure at M go below the vapor pressure. So one way to cause boiling besides heating it up, or in the example they vacuumed out all of the atmosphere surrounding in that big glass bell. Another way you could cause boiling is by spinning something really fast. And in this case, since it's lopsided, the U-tube is lopsided, we have an increase in pressure on the left, a decrease in pressure on the right. It's very possible that if you spin it fast enough, you could see cavitation. Now, the first place you'd see cavitation, which is the vaporization of a liquid, would be here at the top of the tube on the right. But in this case, it's not. These are probably gauge pressures, and the gauge pressure doesn't go below 0, which is required before cavitation will begin. All right, one more example of the U-tubes. This one's open to the atmosphere. We're given the rotation rate here already in radians per second. So this is before. The liquid levels are before. What if we start to spin it at 8 radians per second? Where are the water levels going to stop when it comes into equilibrium? Once the liquid levels adjust to the fact that it started spinning. That's what we're going to try and solve in this third and final example here, the equilibrium water level elevation. All right. So what do we know and what do we not know? Equilibrium. What that means is we're not exactly sure what the z's are going to be. That's our unknown, is the z's. It's going to be, we know it'll rise on one side and fall on the other. What side will the water level rise and what side will it fall? Where's it? Over here, is it going to go up or down? Up. And so it's going to go down over here. Let me ask you this. If it rises, if the water level rises 1 centimeter on the right, how much will it fall on the left? 1 centimeter. That's right. Continuity. It means that you can't have liquid created or destroyed inside of this tube. So if the water goes in the right side, it has to leave the left side by the same amount. And so since we don't know the two elevations, we're going to call this location 1, and we're going to call this one location 2. Well, Z1 is unknown, and Z2 is unknown. But what do we know about Z1 plus Z2? Think about that one. Could we say anything about the sum of those two elevations? 18 plus 18. The sum of those two is going to be 0.36 meters. And so this is just a way of expressing what we agreed on, is that if it rises 1 centimeter in the right, it has to fall 1 centimeter in the left. That the sum of those two elevations will be 0.36. Okay? So we've got our R values. R1 is 0.18 meters. R2 is 0.36 meters. All right. And because of us being smart about what we called 1 and 2, pressure at 1 is 0 and pressure at 2 is 0. So that's going to simplify our rotational flow equation. So we'll cancel out the first term. If we have our rotational flow equation, P1 divided by gamma plus Z1 minus omega squared R1 squared divided by 2G is equal to P2 divided by gamma plus Z2 minus omega squared R2 squared divided by 2G. All right, we cancel out the P1 term, cancel out the P2 term. I'm going to rearrange this equation to be, this was Z1. So it's going to be Z1 minus Z2 is equal to omega squared R1 squared divided by 2G minus omega squared R2 squared divided by 2G. So I just moved Z to the left side of the equation, and I moved this R1 term over to the right side of the equation by adding it. All right. We could consolidate some of the terms on the right-hand side, couldn't we? We could also write this as, we could write it as omega squared divided by 2G, and then just have R1 squared minus R2 squared, since they both had the same rotational rate and the same G that they're experiencing. All right, so what do we know about Z1? From here, I could use this to say Z1 is 0.36 minus Z2. And that might be useful if I had an equation with two unknowns and I wanted to get rid of them. And I do. So I'm going to substitute that in. 0.36 minus Z2 is equal to omega squared divided by 2G R1 squared minus R2 squared. So I just substituted in this 0.36 minus Z2 in place of Z1 because I know that the sum of the two elevations will be the 0.36 meters. Now there's only one unknown in the equation. Everything else besides Z2 is given. So we can solve for Z2. Z2 is omega squared divided by 2g R1 squared minus R2 squared minus 0.36 divided by -2. So that's my expression for Z2. Let me continue that over here with the substitutions. Z2 is 8 radians per second squared, 2 times 9.81 meters per second squared. Now I'm going to put in the radius of 0.18 meters squared minus 0.36 meters squared minus 0.36 meters, and then divide all of that by -2. And now that's going to give me that Z2 is 0.3385 meters. And I can substitute this back into this formula and find that Z1 is 0.0215 meters. Yes, Brandon. It's because when I was at this stage, I had minus Z2 and minus Z2, so there's 2 Z2s. Other questions? So here's the water levels are pretty high in the right and very low in the left. How much have I got over here? Like 2 centimeters. 2 centimeters over here and 34 centimeters over there. Kent, what happens if I spin it even faster than I'm spinning right now? More on the right, less on the left. Okay, so what if I spin it fast enough that I'm at 36 centimeters on the right and 0 centimeters on the left, and then I spin it even more? What happens then, Stephen? Okay, so if it goes, yeah, okay, you got a good point. We're going to make this tube long enough that it doesn't start spilling. So, but, okay, so it gets higher here. Where's that coming from? We're already down to 0 in the left leg. For it to rise another centimeter over here, where's that water? Precisely, yeah. So it's going to start migrating away from the left leg, and so it'll actually be down in the base leg. So if you were actually to substitute in here, we are not going to have time to do the calculations, but if you used an omega of 14 radians per second instead of 8 radians per second, your equation would go kind of like nuts. You'd be solving for your z values and you'd get a negative z value. And you'd think, well, that's not possible. The water level can't be below the base leg. So what that would tell you is that your water is actually in the base leg instead of below it. And so you'd have to come up with a different equation. Instead of saying Z1 plus Z2 equals 0.36, that's not valid anymore once it starts entering the base leg. At that point, you'd need to relate Z2 and where R1 is, because R1 would be changing. If the water level is like here, because it's spinning so fast, then here's 2 and here's 1, then you'd end up with an R1 that's unknown, and then you'd have a Z2. So you'd need to add up the total length of water. You've got 18 centimeters, 36 centimeters, another 18, another 18. All right. With the remaining time that we've got, I'm going to give you a preview of today's lab. So we've still got 4 minutes till class is over. Let me stop the recording, but I'm going to go get the lab device we're using today, and we can talk about that.